All right, we're continuing on the video from before. This is part 2. So we're looking for finding absolute extremes for a function. And so what we do there is the what's called the closed interval method. So I want to find an extreme value, an absolute min or an absolute maximum, the highest or the lowest point for a function f on a closed interval, and where f is continuous. Actually, sometimes when you go looking for things, you don't know there actually is anything to find. We went looking for critical numbers, but there aren't always critical numbers to be found. The extreme value theorem, which you can take a look at in my other video called blank value theorem, but the extreme value theorem guarantees success. The extreme value theorem guarantees that there is an absolute minimum and there is an absolute maximum to be found on this interval. And so that's sometimes nice to know that you are guaranteed success. So we want the absolute extremes for f. Where are those happening and how high are they? And so the procedure that this really follows is step 0, check the prerequisites. This should be of any procedure. Your step 0 should always be checking the prerequisites. Make sure the function involved is continuous on the closed interval that you're given in this case. Next up, you want to find your f prime, simplify it. It's often nice to have it in a big if there's any division at all, have it in one big fraction, one big rational function, or maybe there's roots in there. That's a nice place to do it, because what you want to do next is find out where an f prime is 0, which is going to correspond to that numerator, which is going to happen exactly where that numerator is 0. And you want to find where the derivative is undefined, which is going to correspond to when that denominator is 0. Right. Those are your critical numbers. Places where f prime is 0 and where f prime is undefined that are outside the interval of interest can just get thrown away. We're not interested in them. If there's a higher spot off stage outside of this interval, we don't care about it. So you can throw those out. And then step 4, you take all those critical numbers, plug them back into f, and we want to find the heights. So we take those critical numbers, and we also want to check the endpoints as well, f of a and f of b, because like we saw in that other example in the previous video, you can definitely see the potential for an absolute extreme happening at an endpoint. So if we were doing this problem, if we had the algebra for this problem, for what this curve is, we would find a 0 derivative happening at 1, an undefined derivative happening at 2, and we would have the endpoints -1 and 3, and so then we would have to go, if we didn't have the picture, we'd have to find f of -1, f of 1, f of 2, and f of 3. F of -1 we saw was 0, f of 1 is 20, f of 2 is 10, and f of 3 is 28. If we had the algebraic expression, we get the exact answer. And then you just look through here. Oh, no, it's not 28, it looks more like 18. And as we look through here, 20 is the biggest, 0 is the smallest, done. We don't need to go checking increasing, decreasing. Students tend to do that. That's something you need to identify local extremes, but that's really more work than you need to do to find absolute extremes. So let's work through an example of this. Let's just take a function like this. We're going to find the absolute extremes for f of x equals x to the 2/3 times x minus 5. This may come out nice, this may come out not nice, but it's a fairly typical kind of problem. If I want to go finding derivatives, since this is x minus 5 to the first power, it's going to actually be nicer to expand that out. So that's going to be x to the 5/3 minus 5x to the 2/3. There's my f of x. Oh, I do want to check, I should, for this function, I should really be saying on an interval. Let's say we're going from -1 to 3. Let's take a look at that interval. That's a given problem. So then we want to check whether the derivative is 0. So f prime of x, we've got to find the f prime first. Having in this form is nice. 5/3 x. And there's nothing wrong with doing it with product rule. It's just, it tends to be a little cleaner when you do it this way. So negative 1/3. That's not a great form to go looking for where it is. Derivative is 0 or undefined. So I'm going to simplify this a bit. And when you're dealing with fractions like this, usually one way to do it is to get this negative power here. I want to clear that negative power and hope that it also deals with that, which it will. So I can multiply by x to the 1/3 over x to the 1/3. I also don't like these 3's down here if I can avoid it. So I'm going to multiply by that. And so then when I distribute through across the top, I end up with 5x to the 1 minus 10x to the 0 over 3x to the 1/3. Another thing people will do sometimes, by the way, for there, is they'll try factoring out, and that's fine. You would factor out a 1/3 x to the negative 1/3, and then you would have a 5x to the first minus x to 10. It's the same thing. I tend to like to multiply by things, multiply by 1 rather than factoring, because factoring requires a bit of thinking back and forth and this sort of, what do I need to do to make this into what would this power be, and blah, blah, blah. I don't have to think as hard this way. That's why I like it. And so there's our derivative. F prime of x is 0 when that numerator is 0. So that's x equals 2. F prime of x is undefined when that denominator is 0. Oops, that doesn't work right. When 5x minus 10 equals 0, which implies x equals 2. F prime of x is undefined when that denominator is 0. 3x to the 1/3 is 0, so it's x equals 0. And so we've got our critical numbers of 2 and 0. Quick pause, are they really critical numbers? Yeah, f is defined at 0. This works out to be 0. F is defined at 2. It's not a nice number, but it's a number. And so then we look at f of 0, f of 2 for those two critical numbers. We also got to check our endpoints, f of negative 1 and f of 3. These numbers may or may not come out nice. F of 0 is going to be 0. F of 2 is going to be 2 to the 2/3 times negative 3. F of negative 1 is going to be negative 1 to the 2/3, which is a 1. Because you just negative 1 squared, and then you take the cube root. Notice I'm using the factored form for plugging in. It's a little nicer. I don't have to do as much subtraction. So that's 1 to the 2/3 times negative 4. And then last 3, that's going to be 3 to the 2/3 times negative 2. Well, among these are all negative, and that's 0. So that's actually the maximum right there. The absolute maximum is happening at 0. Among these, it's a bit harder to tell as far as what is the max, which is the minimum, because these numbers are all ugly. Off the top of my head, I don't really know what negative 4 is compared to 2 and compared to this number and compared to this number. If you have a calculator at your disposal, go ahead and use it. If you don't, you could do a few odds and ends to try to figure this out. There's a few other techniques. For example, you could do the increasing and decreasing at this point. Figure out that 0 and at 2, negative 1 and at 3, that this function really, if you look at the positive and negative of this, to the right of 2, it's going to be, f prime is going to be positive. We're looking at f prime here. To the left of 2 will be negative, and then it switches to positive again, and so we have an up, down, up situation. We've already found that the minimum is happening there, although how 3 compares to, height at 3 compares to negative 1, you still can't tell that. This is why doing that is not going to be as useful, because it only gets you so much. It also doesn't quite tell you how those all interact. Well, we know that 2 is definitely less, the height at 2 is definitely less than the height at 3 because of this increasing. But other than that, it doesn't tell you between those two, which is smaller. So sometimes you got to do other methods. For example, I know that 2 to the 2/3 is less than 3 to the 2/3. Unfortunately, I know that 3 is going to be is a larger magnitude than 2. And so I can't quite tell, quite honestly, which one of these is bigger. But between these two, I do know that this is less than 2. And so between the arguments that I made before and here, I know that this is going to be the minimum. There's going to be a minimum at 3. It's a bit of a close call, though, for that one. Either way, even without that kind of a fiddliness at the end, this is our function that we're trying to find extremes for on this interval. Find the derivative, simplify it, find out when it's 0, find out where the derivative is undefined, then plug in those numbers in the f. We never have to actually bother with that increasing, decreasing thing that I did back there. All right, thank you very much.